Hi, I'm Larry Wasserman, an astronomer at Lowell Observatory, and today I'm going to talk about measuring the size of asteroids by occultation. This sounds rather innocuous, but it will get interesting, as we'll see. At least I hope it'll get interesting. I have a number of slides like this with text in them, so my suggestion to the viewers is that let me talk, you don't need to read these. So the basic question, of course, why do we care about the sizes anyway? What good is it? Well, size is a fundamental and basic property of an object. If we know the size of an asteroid, we can determine what's called its albedo. The albedo is the intrinsic surface reflectivity, which tells us something about the composition. A high albedo, which is typical of snows or ices, implies that the surface may be icy, while a low albedo can imply a rocky surface. And on top of that, if we can measure the mass of the object separately, then both the mass and size gives us the density, which is an important quantity telling us about composition. Okay, so why don't we just go to a telescope, take a picture, and measure the size? Well, we can't do that because asteroids appear as points of light. They're too far away and too small. So how do we measure something we can't see? Well, we use a technique called occultation, from the verb to occult, which means cut off from view by interposing something. Occultation has nothing to do with wizards and that sort of stuff. Okay, how does this work? Well, think of every star in the sky as a light source. Then every object moving around the solar system casts a shadow from every star. And as the Earth and the objects move, these shadows move around the solar system. And each shadow is exactly the size of the cross-section of the object. It's a silhouette. And occasionally, a shadow from a star may pass over the Earth. If you're in a location on the Earth where that shadow passes over you, then you see the star disappear behind the object, it blinks out, and then sometime later it reappears on the other side. We say the star was occulted by the object. Okay, what does this mean? Well, if you've got a spherical object, that if you're sitting on the Earth somewhere where the shadow passes by you and you're near the top of the shadow, you'll see a short disappearance. If you're near the middle, you'll see a longer disappearance because the object is wider there. And those near the bottom will also see a short disappearance. We measure the disappearance times accurately, and then since we know how fast the object is moving, and distance is velocity times time, and that's the only equation I'm going to use in this talk, and thus we can reconstruct the size of the shadow. But the shadow is a cross-section of the object. So by measuring the shadow, we measure the object which we can't see. Note that as the shadow passes over the Earth, it generates a strip within which the occultation might be observed. And we call this the ground track. And here's an example. The star and the asteroid casts an instantaneous shadow of its own cross-section, but as it moves across the Earth, it sweeps out a band that we could observe this. If you're in that band, you'll see the occultation. If you're not in the band, you won't see anything. So the trick is to get observers into the shadow, wherever it may be. All right, slight digression. I need to discuss the concept of an ephemeris. An ephemeris is a way of determining where in the sky an object orbiting the sun is at any given time. An ephemeris can be used to point a telescope at a moving object or to do predictions. How do we do this? Well, you start with observations of the object over days or months and hopefully years. From the observations, we mathematically fit something called an orbit. All objects that go around the sun move in an elliptical path. That's the Earth, the planets, the asteroids, And an orbit is 6 numbers that define the shape and the orientation of the ellipse that the object travels in. From the orbit, we can then compute where the object is in the sky, which we call the ephemeris, at any time, the past or future. I note for future reference that bad data, garbage in, garbage out, bad data gives a bad orbit, which gives a bad ephemeris. And what do I mean by bad and what do I mean by good? We'll see. This becomes important. Okay, the shadow is going to cross the Earth, and you got to be there. How do you know when and where? Well, you need 2 things. You need a list of stars and their positions in the sky. Currently, I have in my computer a list which contains about 1 billion stars. That's the stars that might occult something or be occulted. And you need an accurate ephemeris for the desired object. Then we have a computer program that runs the object against the star list. We look for stars that the object will pass close to and see if the shadow of that star will cross the Earth, and if so, where and when. Okay, so we generate a bunch of occultations, but we can't use them all. What happens if a bright object occults a star which is much fainter than it is? So the star disappears when the object passes in front, then there's no noticeable drop, there's nothing to time. So we throw out those events. It's possible that the ground track goes mostly over a part of the Earth that's in daylight. Well, you can't observe stars in daylight, so we have to get rid of those. It's possible that the ground track goes mostly over water. 3/4 of the Earth's surface is water. Can't do that. Well, actually, we can in a way, and I'll discuss that later. But in general, I can't balance my telescope in the middle of the ocean. It's also possible that the ground track goes somewhere we might not want to go. I have a principle that I don't go anywhere to observe an occultation where I'm not likely to come back alive. That's my personal preference. So we don't do occultations in Iran, we don't do occultations in Afghanistan, we try to avoid the Congo. Unfortunately, the list of places where we don't want to go is growing, but that's just the way it is. Also, the ground track may go somewhere without existing telescopes. And in that case, we may have to take the telescope with us if we go to try and observe it. Okay, here's an occultation. It's the ticks across there are 1 minute of time. You'll notice it takes the shadow maybe 15 minutes to cross the Earth from one side to the other. That's a typical velocity. The shadow, according to the arrow, is moving from left to right. And the bright part is daylight, and the stuff over on the right where it's shaded is dark. This one is almost entirely in daylight, and it's pretty much a lot of it over water. That's not a spectacular event. This one hits dark, but it hits dark entirely over ocean, and pretty much the daylight side is water too. So that's not a particularly good event. Let's try a real event that we've done, and then we can see what's involved in doing this in real life. Here's one from 1984. You'll notice the shadow crosses over the United States, a chunk of the Pacific, goes over Asia somewhere, and then goes off the Earth. Okay, that one crosses over the United States. We can do a close-up on that map and see that it's 1982, I'm sorry. This is the asteroid Ursula, 375 Ursula, which crossed this track in 1982. And it came fairly close to us in northern Arizona. At the time, we were trying to observe asteroid occultations, and we actually did observe this one. This is the sort of equipment we took out in the field. You have to go somewhere away from cities, and it's guaranteed that the track will not go over anything useful. So you have to be able to set up in the middle of nowhere. This telescope fit into a truck. We'd haul it up, runs off a motor generator. Back in '82, we didn't have CCDs, so this was a traditional photometer which measures the intensity of light. So we could measure the starlight. Okay, here's what you see. As the star and asteroid approach each other, their light combines, and what you get is this noisy curve as the star and asteroid scintillate in the Earth's atmosphere. And then as the asteroid finally reaches the star, it blocks the light of the star, and the light intensity drops abruptly, basically instantaneously. And then all you see is the asteroid for a while, in this case about 12 seconds, and then the star pops out on the other side, and you see both of them together. So from the time that it's gone, knowing the velocity, we can determine a distance. If you do this at several places over here on the right, you get 2 points separated by that distance. So this was observed successfully at 1, 2, 3, 4, 5, 6 sites. There was another site that did not see anything, and you can see why. It was just north of the shadow, and nothing happened. Its light curve just went straight across. It didn't see anything. Once we have these points that define the endpoints of those lines, we can fit a circle to them mathematically, and that's the size of the object. And mathematically, we get a size for Ursula, diameter, down at the bottom, of 216 kilometers with a formal uncertainty of 3 kilometers. So we've got about a 1% error in the radius. That's pretty good for an object you can't see in the telescope. 216 kilometers is about 120 miles, just for those who think in miles. Okay. An important point is to remember that predictions use measured data. Somebody's gone out and measured the position of the star. Somebody's fit an orbit to the ephemeris. And all measures have errors and uncertainties. I compute the track in the computer, and the question is, does the track actually go anywhere near where I've predicted? The point of this is if the ephemeris or the star are wrong by the equivalent of the diameter of the object itself, 120 miles in this case, then the actual ground track will be 1 track width off from the predicted. Same thing if the star is off, or both. So how far off is one object diameter? We measure the error as an angle, which is defined by the diameter of the object divided by its distance. In this case, that's 120 miles divided by 2 times the distance of the Earth to the Sun, or about 200 million miles. For Ursula, that angle is 0.13 arc seconds, which is not a terribly meaningful number to most people. And that's the equivalent of a quarter, which I am holding up here, 1/4, as seen from 23.5 miles away. So we'd have to measure the position in the star for Ursula to that angle, the equivalent of a quarter at 23 miles away. As it happened, the original prediction had error that was actually 2.5 times that. And the only way we got to the right place at the right time is that we had to make a special effort to remeasure the ephemeris and to remeasure the position of the star and correct the errors. Because in the 1980s, ephemerides and star positions were not as good as they are today. So it took a special effort to actually observe this event. Okay, now what I really want to talk about is measuring the size of the object that New Horizons flew by, the snowman. That, when it was discovered, was called 2014 MU69. That's what the Minor Planet Center gives the asteroids when they're discovered. The project called it Ultima Thule, but that was an invented name. And now that it has a good orbit, it's been assigned a number, 486958. And sometime after the flyby, once it has a number, the discoverer can give it a name. And it's been given the name Arrokoth. I don't particularly like the long number. I never liked Ultima Thule, so I'm going to refer to this as MU69 just for briefness, and I hope you'll remember that that's what I'm talking about. So anyway, an extensive search was made after the flyby of Pluto to find the Kuiper Belt object that the spacecraft could get to with its limited fuel supply. This search resulted in the discovery of MU69, which the spacecraft could actually physically fly by on January 1st, 2019. But to plan that flyby, NASA needed to know its size well in advance. Why? Well, why do they want to know the size of the object? They're going to fly by it. They're going to take pictures of it. Can't they wait? Well, the problem is when you observe an object like this from the Earth, we measure how bright it is, and its ephemeris, remember ephemeris, tells us how far away it is. That tells us the total light that the object is reflected back to us. But if we don't know the object's albedo, its actual reflectivity, we could be looking at a small bright object or a large dark object. Both would reflect the same amount of light back to us. But NASA needed to program the spacecraft well in advance of the flyby, and to do that, they needed to set exposure times. Knowing the size would give us the albedo and determine if it's a small, bright, or a large dark object, and therefore NASA could set its exposure times. So we needed a size so they could set their exposure times. For the planning process, we reversed the process. We guessed a reasonable albedo and derived a reasonable guess for the corresponding size. And that was very small. We're looking at an object that's perhaps 10 or 15 miles across. Well, the only possible way to get a size for this object from the Earth is an occultation. I mean, this thing's 40 times the distance of the Earth from the Sun away, and it's much smaller than the object I just showed you about, which is Ursula. So I was asked to do occultation predictions for this object for 2017. I found 3 possible events. All occurred near opposition, which means that the dark side of the Earth is basically facing the object. So we don't have to worry about daylight. Everywhere the occultation will be is going to be dark. But the major problem here is that MU69 is 15 times smaller than 375 Ursula and 20 times much further away. It's 3.6 billion miles from us. Not close. As a result, the angle that we have to make the prediction to is much smaller. Remember, it was 0.13 for Ursula. This one is 0.00049 arc seconds. So we have to know both the position of the star and the ephemeris of the object to a much higher precision. Let me get out my visual aid again. Now we're talking about not the width of the star, we're talking about the edge of the star, of the quarter, not from seen from 23 miles away, but from seen from Tucson. I hold up this little thing. You're going to measure the angle it covers in Tucson, Arizona, 250 miles away. That's how precise we have to do this if we want to stand any chance of actually doing this in real life. Fortunately, we have 2 spacecraft that arrived just in time. First was the Geyer Spacecraft, which was launched by the European Space Agency. It's measured the positions of 1 billion stars, that's the billion star catalog I referred to earlier, with enough precision so that the errors in the positions of the occulted stars wouldn't matter. It's even small, they do better than we need for this event. Then, in the top of that, the Hubble Space Telescope could be used to observe and correct the ephemeris of MU69. In fact, the Hubble images use the Gaia positions to determine where the asteroid is. So the Gaia positions get used twice. So we were fairly confident that we knew where the ground tracks would be. at least to within a track width or two. And a track width or two is only 20 or 30 miles on the ground. I point out that the positions of the stars measured by Gaia are 10 times better than we need. They're good to 0.00005 arc seconds, equivalent to that thickness of the quarter, not seen from Tucson, but is seen from New York City, 2,500 miles away. Next time you're out, hold up a quarter and ask a friend in New York to measure it and how big it is. It's a staggeringly accurate prediction, a staggeringly accurate number. So we get 3 occultations in the summer of 2017. The first one, these are all, remember, dark. It's dark everywhere. Crosses southern South America and South Africa. The second one hits South America, but is mostly over water. And the third one cuts South America, but even further south than the first one. Okay. Each of these is a very narrow track. Remember, the track is only 15, 20 miles wide. How do you get several observers into the shadow? You need at least 2 or 3. The only way to do this is to set up what's called a picket fence. You put a lot of telescopes in the field, each separated by maybe a fifth to the third of the expected track width, and you spread them wider than the track in order to cover the uncertainties in the star position of the ephemeris. And as I said, mostly in the ephemeris because the star positions are extremely precise. So how do you do this? Well, NASA went out and bought 25 telescopes. These are 16-inch telescopes. They're portable telescopes. They're go-to telescopes, which means they're computer-controlled. And for those who are into this, they're Dobsonian out-as telescopes with a QHY, that's the model number, GPS, which means they're run by a GPS, CMOS, that's a type of CCD, cooled cameras. You cool it so you get the noise down. The camera is operated via a Windows laptop computer. The telescope and camera cooler are powered by a 12-volt automobile battery pack, and the computer runs off its own battery. And in this case, portable is a sort of a misnomer. 4 packing cases per telescope and 2 observers per telescope. Now, this is becoming a major project. Okay, why are these systems a big improvement to the ones we used with Ursula? The Ursula telescope was an equatorial mount, and again, for those who do this sort of thing, that means you don't need to polar align the telescope, which is a pain in the rear. You just point to 2 bright stars, the telescope figures out where it is, where everything else in the sky is, all on its own. The camera allows us to watch the event live on a computer screen. With the Ursula setup, the observer who's guiding the telescope looks in the eyepiece. He's the only one who sees anything. The other person, which was usually me, ran the electronics, and if the drop was deep enough, as it was by Ursula, we had a strip chart recording, and I could tell that we got it by watching the strip chart. On reduction, it has the extra advantage that you can ratio mathematically the candidate star to a field star to remove thin clouds. So if the signal is going up and down a little bit, you can take that out. And to some extent, we can correct for wind shear. That's the advantage of a digital image. It's much easier to find a target, especially a faint target. With the old system, you had to do what's called star hopping, and any senior astronomers out there know what star hopping is, and it's hard. I never was able to do it. I unfortunately went in the field with a guy who was very good at this, and he could find stars walking from one star to another with the telescope. You just sort of go, move it left a little bit till you pick up that star, then move it down till you find pain in the neck. So this way you can just point the telescope to the star. The data is recorded with GPS timing embedded. Also, it records where you are. The old system, you had to go get a topo map. Anybody remember the old? USGS topo maps, and then figure out where you were on the ground. Let's see, we were a tenth of a mile from that intersection. Yeah, that was a mess too. And the old system used a tape recorder with WWV. Those who remember WWV, recorded on one channel. We don't need a motor generator, we have a battery. Motor generator weighed about 75 pounds, battery weighs about 10. On the other hand, you'd think for a $6,000 telescope, they designed something sensibly. The finder goes in from the bottom up, so the stop is at the top. That means if you don't tighten the screws that hold the finder in, and you lift the telescope above the horizontal, the finder can fall out. This is really stupid. And it's mounted way up on the telescope. So if you're short like me, I'm 5'6", and you point the telescope at the zenith, I can't look in the eyepiece without a ladder. I mean, dumb design. Okay, here's a picture with an observer for size. I should give credit to this guy. This is Mark Bowie. He once worked at Lowell. He's now at SWRI, Southwest Research. He was the lead person on this project. He organized it. So everything we did, he's responsible for it. There's the telescope. That's the camera over there. There's the eyepiece way up at the top. Here's the battery. And here's the control computer. And that's all it takes. All of this goes in 4 packing cases to move. Here's an idea of what it takes to get them out of a truck. Remember that to ship these halfway across the world, they load them into a container at SWRI, which is where they're kept. They're trucked to a port. The container is loaded on a ship. The ship goes halfway around the world. It's offloaded in God knows where, and then they're trucked to the site where we put them into trucks, trucks, Ford F-150 type trucks, to haul it to the observing site. Okay, occultation number 1, June 3rd, 2017. Argentina near Mendoza and South Africa. Here's the track. I showed you this one earlier. So the track goes fairly near Mendoza, not too far from Cape Town, as it happens. Here's our picket fence. The green lines are the picket fence. The red line is the center line. The yellow lines are sort of an estimate of our error. They're what are called the 3 sigma lines. And the blue line, which you can see off the left, I think is a 5 sigma line. That's 5 times the estimated error. Now, Mendoza is there, right there. Santiago is there. We were all based in Mendoza. There were a group that went to South Africa. I went to South America. The little blue dots are where the picket fence actually was. The neat thing about this is that if you know where the track goes and you can put a line across it, you can extend the picket fence from South America to Africa and set up one Africa, one South America, one Africa, one South America, and still get everything to work. The trick was you had to be on that line to within 1,000 feet in both continents so that you weren't stepping on somebody else's toes. Okay, so what happened? 12 telescopes in Argentina, 13 in South Africa. 50 observers, 25 trucks to carry the equipment. I was in Argentina, where we also had one local person per team who spoke English and Spanish in case we got stopped by the cops. My Spanish is high school Spanish. It consists of buenos dias and not much else. We had the cooperation for this event of the Argentinian Space Agency, the local police, the Air Force, the Coast Guard. Coast Guard said that if we ran into a problem, they'd send a helicopter to drag us to a hospital, but they couldn't fly at night. Unfortunately, we observe at night, but they did their bit. We had NASA officials tag along. The weather was perfect in both continents, and nothing happened. We found out later, after more data was obtained on the ephemeris, remember I said the ephemeris was the problem? That it was off by just enough that the shadow missed our picket fence. Nobody ever said this was easy. So that's when I say an ephemeris can be bad or it can be good. This one's bad, but only at the 15-mile level. Okay, onward. Occultation number 2. This one is over the Atlantic. Remember I said I could take a telescope over water? This one's over the Atlantic Ocean with SOFIA. SOFIA is the Stratospheric Observatory for Infrared Astronomy. SOFIA, there's the track again. SOFIA is a 90-inch telescope bolted into a 747 aircraft with a hole cut in the side. I won't go into what it takes to get the FAA to approve cutting a hole in a telescope and cutting a hole in an aircraft, making sure that it's still going to fly without killing everybody on board. They're very fussy. Anyway, but the aircraft flies at 45,000 feet. Obviously, it can take data over an ocean, and in fact, it's used to fly over clouds. And the reason it's called an infrared telescope is because at 45, let me back up, the water vapor in the air absorbs infrared radiation. If you can get above most of the water, you can get above most of the blocking of infrared. And this was originally designed to carry a telescope high enough to do that. But it's also very good for occultations. What happened? Well, first off, it's very hard to put a 747 going 500 miles an hour into a 15-mile wide track at the right time as the shadow goes by at 12 miles per second, 43,000 miles per hour. I didn't get to go along with this. I would have liked to, but they missed on this one too. But even if they had gotten a positive result, a single observation of an occultation only gives a lower limit to the size. And I add a note, it turns out they did get one data point, but the duration of the occultation was less than the readout frequency of the CCD, and the dip was so small they didn't recognize what it was till well after the fact. Okay, July 17th, 2017, back to Argentina, to a town called Comodoro Rivadavia. This is our last chance, guys. It's now or never. Okay, here's the overview. The left slide shows where Comodoro Rivadavia is. It's a small oil mining town, sort of the size of Flagstaff, I would say, 40, 50, 60,000 people on the west coast of Argentina. Again, we set up a picket fence just like before, and you can see all the stations. The blue circles are where everybody ended up. So we're going to try it again. What happened? It's basically a repeat performance of the first event, except that everybody this time was at the same location and not distributed over 2 countries, in fact 2 continents. 24 telescopes, 48 observers, 24 trucks, 1 local person per team. And again, we had the cooperation of the space agency, the city government, the police, the Air Force, and the Coast Guard, and NASA officials coming along. This time it was chilly. Winter in Argentina is July, and the area there is windy, which made it seem even colder. And the telescopes are sensitive to wind shakes, so this could be a problem. Several teams, including the one I was with, were set up in rest areas just off the main north-south highway, which connects Comodoro Rivadavia to Buenos Aires. These are big rest areas. They were, maybe quarter mile long and 400 feet deep. But we found that on our practice night, the night before the actual event, we go out and do a dry run exactly as you would for the real event, that the lights of passing trucks were a problem. They shone into the telescope. So the state, whatever state contains Comodoro Rivadavia, actually closed the highway. They put police barricades up for several hours on event night. And if you live on an interstate, as we do here in Flagstaff, think about closing I-40 or I-10 for several hours for a science experiment and see how far that's going to get you. But we succeeded. We got 5 tracks across the object. Hooray. And of course, 19 misses. But that's to be expected. You know you're taking a chance when you do this that you won't be one of the lucky ones. So what do we get? Here are 5 detections from south to north, and they're live. So you can watch each one independently. There's the first one, there's the second one, there's the third one, there's the fourth one, there's the fifth one. So you can actually see what happens in an occultation. The star disappears. This is a very small object, so the star blinks out for about a second, not much more. And the asteroid, which is 100,000 times fainter than the star, is essentially invisible. So when the star blinks out, what you're left with is the sky background. There's no residual signal. And the tracings for each event are shown underneath it. So you can see what you'd see if you were standing there. And if you look at the fourth one from the left and the second one in from the right, you notice the stars bouncing around. That's the wind shake. Fortunately, we can take that out. Here's the team. So they took this picture. I'm the one behind the flag there. So we involved the Universidad Nacional de Patagonia, a bunch of people. CONE is the space agency, the United States Embassy, the mayor and government of the city, the chief of police, the Argentinian Air Force, Gaia, Hubble, NASA. It takes a lot of people to make this work. And we did actually get to go to a reception on the way home. They had a reception in Buenos Aires. We had to spend the night on the way home. And the embassy had us in for a tea and to congratulate us on our hands across the sea science effort. So here's the tracks. This is basically the sort of thing I showed for Ursula. Again, here you can see the dots where the events started and ended, here and here, and all the misses. These are like the one I showed for a miss for Ursula. And it's obvious that this is not a circular object. I mean, just looking at that, there's no way that that could be a sphere. Okay. Well, what about an ellipse? Maybe we could fit an ellipse to the data. Well, it sort of fits, but there's obviously something seriously wrong over here and here. So you notice you fit an ellipse that's sort of 6 miles by 10 miles, but it doesn't fit very well. Okay, there's NASA. It has artists who do this sort of thing. That's an artist's conception of what that object might look like. Remember, this is before the spacecraft went there. We didn't have any idea what it might look like. Okay, well, what if somebody came up with a brilliant idea? Gee, two objects stuck together really fits the data much better, including this extra long chord, which could be both. So you've got an object that's 10 kilometers, that's 6 miles in radius, stuck onto an object that's about 5 miles in radius. Fits the data well. Okay, maybe that's what it is. And NASA came up with this very lovely artist conception of what it might look like. Okay. Here's a picture again of the fit, where the chords are now interrupted by the object. So this one was a real chord. This one's real. That's a miss. I'm pointing at these, but you're not going to see me pointing. That's a miss. That's a miss. That's the nearest miss. This is where it goes behind, comes out, goes behind, comes out. And yeah, it fits the data very nicely. But the kicker is, after the event, we superimpose the object as it really looks. And I'll be damned. It's right. This is the first occultation. I've been doing the occultations for 40 years. This is the first one I got to do where I got proof after the fact that what we measured actually is right in the real world. And I'm very impressed. Notice the scale at the bottom, that's 3 miles. So it really is a very small object. So getting into the right place at the right time was not trivial. Actually, we were fooled. MU-69 had presented a false front to both the occultation and the incoming spacecraft. It rotates such that the object turns this way with time. That's how it rotates in space. So as the spacecraft comes from here looking at it, or as we saw it from the occultation, you only see that snowman aspect. The three-dimensional shape was somewhat of a surprise when the spacecraft passed it and looked back, which we couldn't see from the occultation. We were assuming 2 spheres. The actual shape was something like that. It's actually more of a pancake body, and we were seeing it from this side, looking up. Okay, that ends the talk on this, except NASA wasn't done yet. I was asked to look for more occultations in 2018. Why? They wanted to check on the results from 2017. NASA is very fussy. But they also wanted to check the ephemeris. If you put all those telescopes in the field and only one team observes an event at the predicted time and at the predicted location, it means that the ephemeris that we're getting is still correct. And since the actual flyby, which was in January 1st, 2019, is based on that ephemeris, they wanted to be absolutely certain that MU-69 will be where they thought it would be when New Horizons goes screaming by. And the occultation prediction showed that there would be only one possible event in 2018. Here's the event. It goes over Colombia, Venezuela. The small countries in Africa aren't marked there, but it goes over Senegal, Mali, Algeria, and Libya. Well, I'm not going to go to Libya. I probably wouldn't go to Algeria or Mali. But it turns out Senegal, and I didn't make this decision, I just got to go. Senegal is a reasonably safe place to go. So, 6 telescopes and teams were sent to Colombia, 19 to Senegal. I don't know much about the Colombian trip, except they were all clouded out. And in Senegal, we did the same game. We had 2 astronomers per telescope, plus a local person who spoke French. They speak French in Senegal. And he also spoke the local dialect. Turns out our extra was a geology professor at the nearby university. Really sharp guy, very nice. This time we had a local driver. I had done the driving in Argentina, but this time we had a local driver. And I think I'm very glad we had a local driver. The definition of lanes is somewhat arbitrary in Senegal. They make it up as they go. Anyway, that was a very good idea. And the government, although it's a safe place, so-called, also insisted we carry 2 gendarmes with us, with rifles, to go along to every observing site. Meantime, the government decided that this was a good thing, capital G, capital T, for science education in Senegal, and we were all invited to a press conference with the Senegalese president and members of his cabinet, which was interesting, except they all spoke French, and I speak even less French than I do Spanish, so you got to sit there and look polite while they're talking and you don't understand a word of it. Here it is, us with the president. He's the one in the middle, in the center. I'm somewhere over there. And again, we've got this gigantic team of people. Okay, here's the track right here. This is the 3 sigma limit, the most likely error. This is the 5 sigma error. It's going to occur somewhere in here. We stayed at a Radisson Hotel, 5-star Radisson Hotel, right about there. Gorgeous hotel, middle of nowhere. I have no idea why. And we put 6 teams here at these, and I ended up here in Duga. Very pleasant hotel, not the Radisson, but it was okay. And they fed us. You had 2 choices for dinner. You had to tell them at lunch what you could have for dinner. But the food was excellent. It was very pleasant. And off we went. So only the teams actually got an occultation on this one. Everybody else had clouds. We were on the field at the beginning, and then the clouds moved in. Very frustrating. But that was enough to confirm to NASA that we knew that the ephemeris for MU-16 was correct, and that the spacecraft in MU-69 would end up at the same place in space at the same time, and that everything should work, and it did. And that's basically my talk. Let me take one more minute and point out the picture that was used in the ad for this, of me with the mountain behind me and all the snow, was an occultation by Pluto that I observed in Switzerland. Pluto, unlike these asteroids, has an atmosphere. And you can tell when you get an occultation with an object with an atmosphere, it doesn't fall off abruptly the way a asteroidal occultation does. It falls off slowly, so you get a roll off in the light. And from the rate that the light falls off, you can actually measure the temperature of the atmosphere, and in this case of Pluto. So I have been spending a lot of my time chasing Pluto occultations in various places around the Earth, and that one was in Switzerland. In fact, the Pluto atmosphere was discovered originally by occultation. We had an occultation of Pluto in 1988. We thought we were going to measure the size of Pluto. We discovered the atmosphere. Great surprise. The other thing that you can discover with occultations is rings of planets. The rings of Uranus were discovered that way by observers from MIT and from Lowell in 1977. They thought they were going to study the atmosphere of Uranus the same way we studied Pluto, but there were these 5 drops before the atmospheric event and 5 drops after that reversed in time. And the only thing that made sense for that was a ring system around Uranus. So, surprise. Since then, we've discovered 2 asteroids, just by chance, that had rings around. And nobody had ever predicted that asteroids might have rings, but we now know that there are 2, both discovered by occultation. So it's a really neat technique, and you never know what you're going to find. And at this point, I will take some questions, and I have a few here. Let's see. The first one says, I'd like a computer-controlled telescope so I don't have to polar align. I found one from Orion. Any opinion? I'm afraid I'm not an expert on this sort of thing, but I would recommend that before you buy anything that you find an astronomy club in your neighborhood. They are experts on this sort of thing, and they can advise amateurs, and you might want to try a couple of mounts and telescopes with them. So don't take my recommendation, but I would definitely find an astronomy club and take theirs. Somebody else asked, was the picket fence sizing adjusted on the 3rd try? Yes, it was. We felt we had a better handle on the ephemeris, and we felt we could tighten up the picket fence, which is why we were able to get 5 cords. I will say that some of you may have noticed that there was a hole in the picket fence. It looked like there was a cord there that was missing, and it was. One of the teams, whose name shall go unnamed, did an unforgivable sin. They got on the target. They were on the target properly, but they decided it was cold and that the telescope would do its thing and they didn't have to watch it. In the meantime, they decided that they would go into the truck and stay warm. But in the meantime, the telescope was not tracking properly. It wasn't following the stars properly. So with time, the field drifted out so that they were no longer looking at the star. So when the shadow went over them, and it did go over them, they weren't looking at the right star. Needless to say, they have been drummed out of the Honorable Society of Occultation Observers and will never be asked to do this again. So we could have had 6 scores, but we got 5. Let's see, was anything learned about the stars that were occulted? No. We know that they weren't probably double. If you have close double stars, you can sometimes get 2 occultations as each star gets occulted, but neither would double. And let's see, do you have a graph to show the drop-off in the curve caused by atmosphere rings? I don't have one here right now, but basically think of, you get dip, 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 and then nothing, and then you get the fall off as you go into the atmosphere. And then as it comes out the other side, you get the identical dips. And the interesting thing, particularly about Uranus, is that one of the rings is fatter than the other. So it's a wide dip. It was the first one to disappear and the last one to come out. So if you folded the thing back over on itself, you got a mirror, you folded it back on top of itself. And that's how they knew they were rings, because they appeared in reverse order on the other side. The Pluto one just rolls off slowly. It takes maybe 10, 15 seconds to drop to its minimum, and then it reverses as Pluto as it comes out on the other side. How long did it take to ship all the equipment to Argentina and South Africa? I don't know. I don't know. It was there when we got there, but it was handled by the people in Squarry. The equipment stays there. I've done an occultation with them in the United States, and in that case, they loaded it into a big U-Haul truck and drove it cross country. We did one in Texas, and they hauled the occultation equipment from Denver down to near San Antonio. So great fun. Anyway, one other statement. Astronomers don't do occultations of asteroids much anymore unless they're very special, like this one, or maybe an object in the Kuiper Belt that's far away. The amateurs, the equipment has become so cheap and so readily available, the amateurs have taken this over, and they do this, and they don't get paid, and it's a little hard to write a grant to NASA asking for money for something that the amateurs are going to do free. So we do the exotic stuff like this one, or Pluto occultations, and leave the generic asteroid events to them. Anyway, there are no more questions apparently. So I thank everybody for listening and putting up with me, and I'll say goodbye. Thank you very much.